Let me write down the Polyakov action. So we have S equal to minus 1 over 4 pi alpha prime. This is just a constant. Then we integrate over d squared sigma. We have the square root of minus the determinant of the metric tensor g alpha beta. So here we just have g, the determinant. Then we have the inverse metric tensor g alpha beta with upper indices. Then we take the partial derivative with respect to sigma alpha. So we just write d alpha x mu d beta x nu eta mu nu. And remember that this is the metric tensor of the surface that we are considering. So this is a 2 by 2 tensor. Whereas this is the d by d Minkowski metric. It contracts with the indices of the coordinates. So these are d-dimensional objects. Okay, so with the choice of the flat metric, so instead of having g alpha beta, for example, if we set g alpha beta equal to eta alpha beta, which is something we can do, and we showed over the past few lectures, because we can take advantage of gauge symmetry and set g alpha beta equal to eta alpha beta. This is something that we can do because by making an appropriate transformation, with this transformation we can set g alpha beta equal to eta alpha beta. So in that case, we know that the determinant g is actually equal to minus 1 with this choice. So I should write eta equal to minus 1. So this is the determinant of eta alpha beta, and therefore the action S can be written as minus 1 over 4 pi alpha prime. Then we integrate d square sigma eta alpha beta d alpha x mu eta beta x nu eta mu nu. So remember that this eta alpha beta is not the inverse of this matrix here, because this matrix is d by d, whereas this is 2 by 2. So you have to keep that in mind. And remember also the notation that we can use. So instead of writing these products, we can simply write d alpha x dot product d beta x like this. And then if we want, we can also rewrite all these with a more concise notation, because eta alpha beta times d alpha x dot product d beta x can also be written like this. So we have the same constant minus 1 over 4 pi alpha prime integral d square sigma, and then we can write it like this: d alpha x dot product with d alpha x like this. So this is more compact. And the equation of motion becomes, so remember that we derive the following equation of motion: d alpha square root of minus g alpha beta d beta x mu equal to 0. Well, if you choose g equal to eta, this will simplify like this. We have d alpha eta alpha beta d beta x mu equal to 0. And of course, this implies d alpha with the upper alpha in this case, x mu equal to 0, like this. And this is a free wave equation if you think about it. It's a simple equation, but we also have to make sure that the equation of motion for g alpha beta is satisfied. Remember that we also derived an equation after taking the variation of the field. And you can consider those as constraints. Those are the constraints related to the equation of motion. And also in this case, there are some constraints. Now let's try to understand what the constraints are in this case. Well, it is just simply something that you can understand if you take the variation of this general action here. We take the variation with respect to g alpha beta. So the variation of the action can be written like this. So we take the variation by assuming that It is the field G alpha beta which is varying, and of course also G alpha beta like this. They will change according to some variation because the field changes. We are varying the field. We are taking small perturbations of the field and see what is the result on the action. So the change in the action, in this case, I'm considering the change in the Polyakov action. So I'm really taking the variation of this. So we are concerned with this part of the action because there will be a change in the determinant and also a change in the inverse metric tensor. So the variation of the action can be written like this. We have the same constant minus 1 over 4 pi alpha prime. Then we have integral d squared sigma. And then we have the square root of minus g. And then we vary g alpha beta. Then we have d alpha x dot product with d beta x. Then you have to take the variation of the square root of minus g. So we have variation of square root of minus g. And then you have g alpha beta times d alpha x dot product d beta x. Let me change the name of these indices, alpha and beta, and I can do that because they are just dummy indices. So you have g rho sigma d rho x dot product d sigma x, like this. And now we have to remember how to take the variation of the square root of minus g. This is quite simple. So you have minus 1 over 2 square root of minus g variation of g, but this is also equal to square root of minus g divided by 2 dg over g, and dg over g can also be rewritten, so you have the square root of minus g over 2 g alpha beta dg alpha beta like this, and this is also equal to minus square root of minus g over 2 g alpha beta with lower indices and dg alpha beta with upper indices, like this. Now if we substitute this here, the action, actually the variation of the action, ds, can be written like this. So you have minus 1 over 4 pi alpha prime integral d squared sigma. Then you can factor out square root of minus g. You can factor out dg alpha beta. And then you have d alpha x dot product d beta x minus 1 over 2 g rho sigma. And then you have g alpha beta d rho x dot product d sigma x, like this. Now we will call this term here in parentheses, we will call it t alpha beta. And in order for the equation of motions for g alpha beta to be satisfied, we have to set t alpha beta equal to 0. And if you check, t alpha beta can also be written as minus 2 over t, where if you recall, t is just equal to 1 over 2 pi alpha prime. Basically, minus 2 over t is just minus 4 pi alpha prime. It's the inverse of this constant here, right? Then we have the derivative of the action with respect to g alpha beta with upper indices, and then we multiply by 1 over the square root of minus g. From general relativity, well, this kind of definition here is used to define the stress energy momentum tensor, or simply stress energy tensor or energy tensor, also energy momentum tensor. So you can hear several names, but they refer to this tensor here, which is very important in general relativity, if you recall. In this case, we set it equal to 0 because we don't have any other object with respect to the string. So the energy momentum tensor of the string should be set equal to 0. Therefore, we must set this equal to d alpha x dot product d beta x minus 1/2 g rho sigma g alpha beta. Then we have d rho x dot product with d sigma x, we set it equal to 0. And if we want to write the equations more explicitly, we can write t01, for example, which is equal to t10. And remember that alpha and beta can only take two values. So alpha can either be 0 and 1. Beta can be either 0 and 1. So these two will be the same. And it's quite easy to calculate them. So for example, let's calculate t01, and you can show that it will be equal to t10. So we have to set alpha equal to 0. So we have d0x dot product d1x, and then we have minus 1/2 g rho sigma. So in this case we are going to use the fact that g will be equal to era. So let me write down era here, and also here I will write era. So in this case we have era rho sigma, and then we have era alpha beta. So in this case it's era 0,1, which is equal to era 1,0, and that's equal to 0. So it's going to simplify quite a lot. This is equal to 0, but also this is equal to 0. So we get d0 x dot product d1x equal to 0, but this is also equal to x dot product x prime equal to 0, just a different notation. Then we can calculate t00, which is equal to d0x dot product d0x minus 1/2 era rho sigma era 00 d rho x dot product d sigma x. Era 00 is equal to minus 1 according to the convention that we have used. So we take the signature minus 1, 1. In this case, it is of course a 2 by 2 metric tensor. So the coordinate related to time, we will attribute to it a minus sign. And then here, the special coordinate, we will attribute to it a plus sign. So we have plus 1 in the diagonal. And it's quite simple now to rewrite this. This is equal to x dot from here, dot product with x dot, which we'll simply write as x dot squared. Then we have minus 1/2, but we also have another minus, so we can write plus 1/2. And then we have era rho sigma times this, and we can rewrite that as minus x dot squared plus x prime squared. And of course, this is equal to x dot squared plus x prime squared over 2, and we have to set it equal to 0. It's also easy to check that t11 is equal to t00. And this is where we'll stop for this lecture.